Hi there, everyone. Welcome to your week 3 lecture. I do need to apologize. First, I was not able to get this done before I left for the weekend, and so I'm having to do this from my house. And I'm a little embarrassed. I wanted to be in our first library. This is our second library, and it's fine, I guess, but the first library is much nicer and it's being cleaned. So hopefully this is okay. It's not too much of a distraction for you, hopefully. So I do apologize about that, but we'll get going here. And of course, we'll start with the chemistry cat joke. So I'm just going to go ahead and let you take that in. Great. All right, we have been talking about the history of the atom. We, together in breakout rooms, put together a document that ended with Rutherford. After Rutherford comes Bohr. Now, real quick before we get into the Bohr model, yeah, I will sometimes show you these slides that have this yellow background, and the intention is for you to pause and kind of think through and answer this question. There's no way for me to know if you do that or not, but I am putting these into the lectures for a reason, and so that's my kind of hint to you when it comes to upcoming quizzes or tests in terms of material that you're going to want to know. So here we're asking you to look at that image and talk about which scientist would have that model. And that's Thomson. Remember that both the Greeks and Dalton would have pictured a solid sphere, and that's not what we have here. We have components, right? They originally thought an indivisible solid sphere, and there are both positive and negative parts to this one, so it couldn't be Greek or the Greeks or the Dalton model. And it's not Rutherford, because Rutherford talked about a tiny little nucleus and the electrons existing in empty space around it, and that is not what's being depicted here. So as you think through kind of process of elimination, this would be Thomson's plum pudding model. Now, when I asked you to draw what you think an atom looks like, and again, not right or wrong, I just want to see where you're all at, but a majority of you gave me something that looked like this. Some of you gave me even a little more detail and gave me something that looked like this. And there's a reason that so many people, when they envision an atom, give the Bohr model. That's incorrect, although it's interesting. I will use the Bohr model to help illustrate things throughout the class. So obviously there's some, some correct parts to this model, but it's not quite the complete vision of what we now see an atom to be. And as I mentioned as well, like they use this everywhere. I think the Department of Energy has this or something similar as on their logo, even though it's not quite correct. So the idea is, how do we get here? How do we get to the Bohr model? And how are we going to then move on to our kind of final vision of the model of an atom? So it starts with Planck. And what he proposes is that very specific amounts of energy are being associated with an atom, and we call those quanta of energy. And so early on, he saw that. A little bit later, Bohr kind of ran with that idea, and he specifically said that electrons can possess only certain amounts of energy, quanta of energy, and that therefore they can only be existing at certain distance from the nucleus. And so his is called the planetary model, and I will show you why that's the case, but I think you can kind of picture it already. And again, what he's saying is, if we have that atom right there, so the nucleus is going to be in the middle here, so we have protons and neutrons in the nucleus. Here's one energy level, and here's a second energy level that electrons could exist. They're at very specific distances. So again, it's circular in order to maintain that specific distance. And what he's saying is an electron can exist at this distance or at this distance, but not in between. And that's a little bit of a weird idea, and it'll take us into next week, really, to kind of wrap our heads around what that quanta idea means and how can an electron just exist here and then all of a sudden exist here. So that's what we'll talk about through the last model next week. But this is the planetary model. So getting back to this idea of these quanta of energy, you have that chart on the left. I actually think a better analogy is this. So if you were to think about kind of walking up this ramp, you could exist at any point continuously along this. Now compare that to steps. You have to exist on this step or this step. You can't be hovering in between those two steps. And that's what we mean when we talk about electrons existing at very specific amounts of energy and very specific distances from the nucleus, again, according to the Bohr model. And we will work through that model and improve it into next week. So this is what we mean by continuous energy versus these quanta of energy. So here's that final look at the model, Bohr's model. So you have the nucleus still that is coming from Rutherford. We've got the electrons, again, still existing in this empty space around the nucleus. But the idea is that there's specific orbits and energy levels in which these electrons will exist. They need to possess a very specific amount of energy in order to do that. And again, this is why it's called the planetary model. But what we will realize is that electrons really don't behave like planets where they orbit in a specific path. So we need to get that out of our head. So they don't orbit, even though we are going to continue to call these orbitals as we talk through how electrons reside around an atom. So then what was his evidence to come up with this model? And it comes down to light. So you will see that in our lab this week, we're going to involve light in different colors, whether you're doing the in-person or online version. And so that's what he was working with. And specifically, it was these emission line spectrum is what he was seeing. And I'm going to assume that a number of you have been exposed to this type of thing, especially in earth science or astronomy. But what you see is that for each element, we're getting unique spectra being formed as these emission lines form. And the idea that he was coming up with here is that it must be because of those very specific amounts of energy electrons possess, they must be able to put off these specific emission spectra. And so we'll get into that over the next few slides. But this is what he was seeing that eventually led him to that conclusion. So before we kind of come back to those spectrum, let's just talk about light in general. And so there's a couple of slides worth of notes here, but this is what you need to be using when we ask you to explain what's happening in our flame test lab. So to start, if we have an electron in its lowest possible energy state, and that means all the electron, depending on which atom we're dealing with, when they're in their lowest possible energy, this is called the ground state. It's kind of like the ground floor almost. Now, it doesn't mean that every single electron is right next to the nucleus. We will learn that really there's specific numbers of electrons that exist in different orbitals. But for now, it just means that all of the electrons are in their lowest possible energy. So let's say helium as an example. So we'll have two electrons and they'll both be residing in that closest energy level to the nucleus. Now, if one of those electrons or multiple electrons absorb a specific amount of energy, so the right amount of energy, they can move up to a higher energy level. So as we move away from the nucleus, those energy levels have higher and higher amounts of energy associated with them, meaning that that electron would need to absorb energy in order to move up. Now, that situation, which we call the excited state, is unstable. So an atom wants to be stable. It wants all electrons in the ground state. But if we force energy upon one of those electrons, it'll move up if it's the right amount. But as soon as it can, it wants to move back down to ground state. So you'll notice here energy, we're going to be using heat in our lab, but you could talk about light or electricity as a form of energy. So you'll notice that when that electron absorbs that energy, it moves up. Again, it's unstable. It does not like being in that configuration with extra energy. But because it absorbed that right amount of energy, it moves up. And again, when you think about this, again, it absorbed the energy and it had to be a very specific amount to then exist in that higher energy level. There was no in between. So the electron was either in that first energy level, all of a sudden it absorbed enough energy and it's then existing in the second energy level. So it's not continuous. Even though I'm going to draw lines where I'm saying, oh, it moves from here to here, that's not a great way of showing it. It's hard to show it differently. So be careful of the continuous versus the quanta of energy. So now you'll notice that we've got one electron in its ground state still, but the other electron is in this excited state. So as I've been implying, that electron and the atom in general does not like having extra energy associated with its electrons. And you do need to be careful. I hear a lot of times students saying that the atom moves to an excited state. It's the electrons around the nucleus that are moving to an excited state. So we're going to get that electron to fall back down. But because it absorbed energy to exist in that higher energy level, it's not going to be allowed down into a lower energy level. So for example, because this electron has more energy associated with it, it's not allowed down in this energy level until it releases that energy that it originally absorbed. So that's where we get those emission line spectra. And that's where, as you start to do the lab, you'll see this is where we get some of the cool colors that you see. So yes, the electron wants to move back down to its ground state, but it has to release that energy first. And in this case, it's going to be in the form of photons and light. So now, because it released that energy, it's allowed back down into the ground state. And then if it were to absorb energy again, it would move back up to an excited state. Again, it has to be the right amount of energy. So when we talk about the right amount of energy being released, those are those lines on the spectra that we'll come back to here in just a moment. Actually, right now. So again, each of those lines represents a very specific fall for an electron. We showed you just moving from first energy to second energy level and back down. But really, the energy levels around an atom go on for infinite. Now, of course, at some point, if enough energy is added to an electron, it just goes away, and we get an ion forming. But even within the energy levels, there's a lot of potential moves, a lot of potential absorptions and releases that can happen. So that's why we get multiple lines. So again, the simplest little animation I can do here is there's an electron in a ground state. It's going to absorb energy. It moves to an excited state. That's unstable. It wants to move back down, but it has to release the energy first. As soon as it releases that right amount of energy, it's going to move back down to ground state. And if that energy is within the visible light spectrum, we will see a line in our emission spectrum. So if you were to just look at a light source right now, somewhere around wherever you are, the light coming from that source is just an electron doing that, well, many, many electrons doing this over and over and over. So again, coming back here, we've got hydrogen being excited, so that's going to be utilizing electricity. And what we can do is we can send that light through either a prism or a diffraction gradient, but we're pretty much going to split that light. The reason it splits is because the photons have differing amounts of energy because they have differing amounts of, or differing wavelengths. And so because it takes a little bit longer for some of those light sources to move through, that's why we get the splitting of those spectrum. And so again, there's the hydrogen, and why the multiple lines? So again, as I was alluding to previously, if we've got hydrogen here, there's the nucleus, so one proton, maybe one neutron, but likely not. Let's just draw some random energy levels here. Again, these would each exist with very specific amounts of energy and very specific distances from that nucleus. So let's say I've got an electron, since it's ground state, and again, it would not, I'm going to draw a line. It's not continuous like that. Ultimately, if it absorbed energy, it would exist up here. So again, it absorbed energy until it was able to move further away from the nucleus. And then when it moves back down, it's going to move from the second to the first energy level, and it's going to release a specific amount of energy. And maybe that's this line. So every time an electron moves from first to second back down, we get that line. Notice that instead, maybe this electron could absorb a differing amount of energy where it's allowed to move all the way up to this third energy level and then fall all the way back down to the first. And that might represent this line. So again, because you have unique combinations of those electrons moving up and down and releasing those specific amounts of energy, we get differing lines on the spectra. So that's why you get those multiple lines. And again, I'm not going to spend too much time here. I did want to point out, and it's going to be important for your lab, is that as I move from violet up towards red on this spectrum, that we're actually decreasing energy. The other way to think about it, and again, this is just, it's a little bit confusing, but the smaller the wavelength, the greater the energy. So violet is going to be the most energetic photon that you'll be seeing that's reaching your eyes, whereas red is the least energetic. So there's a question on the lab that you'll need to utilize something like this. And again, we can look at a bunch of different spectra. Each is unique. And when you see the overall color from each of these, you're just seeing the overall combination of those different lines. And again, we can figure out exactly on this wavelength where the color is falling and how energetic those photons are. So this maybe puts in perspective if you're a classic rock fan, this famous album cover. You might realize that white light is actually just a combination of all of the wavelengths of light. So let's quickly just double check in Bohr's model of the atom. Electrons in the energy level closest to the nucleus would have blank energy compared to the electrons further away. And again, in this case, it's lower amount of energy the closer to the nucleus. And again, remember that the electrons have to absorb energy in order to move further away and exist in a higher energy level. One more analogy here, just this idea of quanta and the spectrum lines that you see. It's kind of like maybe like floors in a hotel. And so you can be on the first floor, the second floor, the third floor. You don't exist in between. So that's the same idea as that's happening up here, because they have very specific amounts of energy required to move into each of these different energy levels. We get very specific, unique lines on the spectrum. Finally, here's the visible light spectrum, which we've been talking about, and you just saw from violet all the way to red. There's other potential jumps that are happening here. So notice that here you've got a jump that possibly all the way from the 6th energy level all the way down to the 1st. That's very energetic. That is a lot of energy being released. And that is actually ultraviolet radiation. So obviously we get a lot of ultraviolet radiation from the sun. So there's a lot of energy associated with a star, and all of that energy having electrons move way up and fall way down gives us UV radiation, but that's not visible to us. And so while you are going to have atoms giving off ultraviolet, you would not realize that. Those don't fall into the spectrum and they don't form a line. On the other end of things, you have infrared. This is mostly just heat. But again, atoms have the ability with smaller jumps with less energy to give off infrared radiation. So your visible light spectrum falls in between ultraviolet and infrared. And again, we can't see UV, we can't see the IR infrared. So we're only seeing the jumps that are causing visible light. One more check. And again, you got to be careful here. It is a specific amount of energy that must be absorbed. So not just any random amount. It's got to be a very specific amount of energy that allows that electron to move up into higher energy levels. Almost like a lock and key. You have to have the key, which is the correct amount of energy, in order to undo the lock and get into a specific energy level. Here's just a quick animation if you want to play around with it. If you're a visual person, this might help explain some of the things that are going on. And I just wanted to end real quick here with a connection to fireworks. So when fireworks are being made, they are being packed with very specific compounds based on the spectrum that those compounds give out. So you'll see in your lab that we're going to be dealing with some of these metals, but these metals and their electrons give off very specific and unique colors because of their unique electron jumps within their configurations. And so you know, those people making fireworks can have very specific shows in terms of the colors that they want. It all has to do with chemistry. Okay, so that is your week 3 lecture. If you are an honors student, you're going to have an extra lecture after this. But for the rest of you, this is it. So again, just understanding the Bohr model and how that relates to light is the biggest thing from this. Thank you for sitting through this. I appreciate your attention. Until next time.